Imagine standing on a cliff at night, watching the world sleep beneath a calm, star-filled sky. Everything feels peaceful, untouched, eternal, but what you cannot see, what none of us can see, is the invisible force surrounding our planet every second of every day. A vast magnetic shield, stretching tens of thousands of kilometers into space, bending the solar wind around us like water around a stone. Without it, Earth would be unrecognizable. Without it, life as we know it would not exist. This shield is not made of metal or stone. It's not something we built. It's something the planet itself creates. An unseen guardian forged in the darkness beneath our feet. Far below the continents and oceans, deeper than any drilling machine could ever reach, lies Earth's outer core, a swirling ocean of molten iron and nickel. It moves, churns, and flows like a living creature. And as it moves, it generates electrical currents powerful enough to create a magnetic field that wraps around the entire planet. This is the geodynamo, Earth's hidden engine. Even though we cannot feel it, this magnetic field is constantly working to keep us safe. Every second, the sun sends out a storm of charged particles at unimaginable speeds. The solar wind, if those particles reached Earth's surface, they would strip away our atmosphere, destroy our ozone layer, and fry the delicate molecules that make life possible. But instead, they hit our magnetic field first. The shield bends them aside, redirects them toward the poles, and sends them into the upper atmosphere, where they ignite the sky with glowing curtains of color, the auroras. These shimmering lights are not just beautiful displays. They are visible proof that our planet is fighting for us. We rarely think about this protection. We go about our lives as though the sun shines harmlessly, as though the space around us is empty. But every moment, a cosmic battle is happening just beyond the sky, and Earth's magnetic field is the only reason that battle has not reached us. Beyond shielding us from radiation, this field does something else just as important. It helps our planet stay stable. It shields the atmosphere from erosion, helps maintain the climate, and even influences animal migration. Whales, birds, turtles, bees, all navigating by sensing Earth's magnetic lines. The magnetic field is not just a shield. It is a guide, a stabilizer, a silent architect of life's evolution. Without it, Earth might look more like Mars, cold, barren, stripped of its air. But this guardian is not fixed. It's alive. It shifts, drifts, stretches, and bends. And in the long timeline of our planet, it has done something far more dramatic. It has flipped. North becomes south. South becomes north. The entire magnetic field reverses. This has not happened once or twice, but hundreds of times over Earth's history. The poles have switched places, moved across the globe, multiplied into several north and south poles at once, and then settled again. Each reversal took thousands of years, slow to us, lightning fast in geological time, and each time Earth changed. Not catastrophically, not instantly, but undeniably. When the poles reverse, the magnetic field weakens. Sometimes it weakens by as much as 80 or 90%. The shield becomes thin, patchy, fragile. More radiation reaches the surface. Auroras dance near the equator. The sky glows like a giant warning sign. The world becomes a place of strange lights and strange forces. This is not speculation. The evidence is written in the rocks. When molten lava cools, the iron in it locks in the direction of Earth's magnetic field, like tiny compasses frozen in stone. Layer by layer, these rocks record the history of our planet's magnetism, a magnetic diary stretching millions of years into the past. And what we've learned from that diary is clear. The poles flip when the field weakens, and when the field weakens, the world changes. The last full reversal happened about 780,000 years ago, life survived. The planet endured. But the next reversal is not a question of if, it is a question of when. Because something is happening right now. Something scientists are watching with growing concern. Earth's magnetic field is weakening. In the last 150 years, it has lost nearly 10% of its strength. The magnetic North Pole, once slowly drifting across Canada, is now racing towards Siberia at nearly 50 kilometers per year. Strange anomalies have appeared, like the South Atlantic Anomaly, a vast region stretching from South America to Africa, where the magnetic field is unusually weak. Satellites passing overhead in this zone get bombarded with radiation. Some malfunction. Others shut down temporarily to survive the storm. Something deep inside the planet is shifting. Some scientists believe the weakening is a sign that Earth's magnetic field might be entering the early stages of a reversal. Others argue it may simply be a temporary wobble, one of many fluctuations the field has gone through over millions of years. But no one knows for certain. The core is too deep, too inaccessible, too complex for us to observe directly. All we know is this: the shield is changing. And if it continues to weaken, if the poles continue to wander, if the anomalies continue to grow, then we may be witnessing the beginning of something Earth has not experienced since early humans first walked across the savannas: a magnetic flip. The sky would glow, radiation levels would rise, satellites would fail, navigation would distort, and the world we know, the stable, predictable world beneath our feet, would begin to shift in ways we have never experienced in human history. This is not fear, it is physics. And in the next part of the story, we dig deeper into Earth's past, where the clues to our future are written in stone, waiting for us to read them. If you could peel back the layers of Earth like the pages of an ancient book, you would find its magnetic history written in stone, not in words or symbols, but in the alignment of tiny particles, microscopic grains of iron that once floated freely inside molten lava. As that lava cooled and hardened, those grains froze in place, locked forever in the direction of the planet's magnetic field. At that exact moment in time, each rock became a fragment of Earth's magnetic memory, a timestamp from deep history. This science is called paleomagnetism, the study of old magnetism, and it has revealed a truth so strange, so unexpected, that it transformed our understanding of the planet. Earth's magnetic field flips entirely. North becomes south, south becomes north, and it doesn't happen on a schedule. The record preserved in volcanic rocks shows that reversals occur irregularly, unpredictably, sometimes separated by millions of years, sometimes much closer. At times, the field remained stable for long stretches. At others, it flipped again and again in rapid succession, as if the planet's dynamo deep below were experiencing a kind of chaotic heartbeat. There is no rhythm, no cycle, no pattern we can rely on. The last full reversal, the Brunhes-Matuyama reversal, happened about 780,000 years ago, long before written history, long before agriculture, long before modern humans took their first footsteps. And yet, the evidence of that reversal is everywhere, in the rocks of the ocean floor, in frozen lava flows on every continent, in the magnetic signature of mountains that rose long after the flip occurred. But the Brunhes-Matuyama event wasn't fast. It unfolded over thousands of years. During that time, the magnetic field weakened, grew unstable, sprouted multiple north and south poles, and only then settled into its reversed state. Nothing about that process was gentle, but nothing about it was catastrophic either. Life adapted. Earth continued its long story. Yet even that long reversal wasn't the most dramatic event we've uncovered. Around 41,000 years ago, something unusual happened. A brief, intense magnetic flip, known as the Lachamp event. Unlike full reversals that take millennia, this one lasted only a few hundred years. And at its weakest moment, the magnetic field dropped to just 5% of its current strength. Imagine that. A global shield almost switched off. Radiation surged into the atmosphere. Auroras may have been visible across the entire planet. Ice core samples show spikes in radioactive isotopes, fingerprints of cosmic rays that reached Earth's surface more easily during the weakened field. Some scientists even suggest that the Lachamp event may have influenced climate patterns and contributed to the decline of Neanderthal populations, though this remains debated. But one thing is clear: even during that dramatic weakening, life endured, species adapted, human ancestors survived and continued their migrations across the globe. The planet changed, but it did not fall apart. Still, these paleomagnetic records show us that Earth's field can weaken far more than it already has, and that such weakening is often tied to an upcoming reversal. And this is where our attention shifts from ancient rocks to something happening right now, something modern technology has been whispering about for decades: the South Atlantic Anomaly. Stretching from South America to Southern Africa, this vast region is a weak spot in Earth's magnetic field. The weakest spot on the planet. Satellites passing overhead are bombarded with radiation. Some instruments glitch. Others are switched off deliberately to avoid damage. It's like a crack in the armor, a thinning in the shield. Scientists studying Earth's core believe this anomaly may be caused by an unusual patch of dense rock sinking in the lower mantle, altering the flow of molten iron in the core beneath it. That disturbed flow weakens the magnetic field above, creating the anomaly we observe today. What makes the South Atlantic Anomaly especially concerning is that it isn't stable. It's growing, it's drifting, it's splitting into multiple weaker regions, and as it changes, the global magnetic field continues its slow decline. Over the past 150 years, Earth's magnetic field has weakened by nearly 10%. That number may seem small, but in geophysical terms, it is enormous. The kind of change that could signal the beginning of a much larger shift. The weakening isn't uniform either. Some regions are losing strength far faster than others, hinting at deeper turbulence inside Earth's core. To scientists, this trend raises a question that echoes through every paleomagnetic study. Is this just a fluctuation, or is it the early phase of a reversal? We cannot say for certain Earth has experienced temporary dips in field strength before without flipping. But it has also experienced dips of similar magnitude as the early stages of past reversals. Paleomagnetism tells us that the dynamo is capable of sudden, unexpected changes, and that reversals often begin with a widespread weakening of the global field, irregular pole movements, and spreading anomalies. All three are happening now. This doesn't mean a flip will occur in our lifetimes. It could be centuries away, it could be millennia away, or the field could stabilize again, recovering its strength as it has in the distant past. The core of our planet is a place of churning metal and unpredictable motion. We cannot watch it directly. We can only read the clues it leaves behind. But the message written in stone, in ice, and in satellites above our heads is clear. Earth's magnetic field is not permanent. It has changed before, it is changing now, and it will change again. And as we follow those clues, the story begins to shift from ancient rocks and lost ages to something far more immediate. What happens when the magnetic field begins to enter the chaotic stage of a reversal? What will the world feel like when the shield that has protected us for billions of years begins to dim? The past has spoken. Now we turn to the mechanics of the flip itself and the strange turbulent phase that comes before the world's magnetic poles switch places. Deep beneath your feet, past the soil and rock and ancient crust, past the mantle where stone moves like warm wax, lies a world you will never see. A world of fire and metal at its Earth's outer core, a vast sphere of molten iron swirling in endless motion. If you could stand there, though no human ever could, you would witness a churning ocean of liquid metal hotter than the surface of the sun, rising and falling in great convective waves. Columns of molten iron spiral upward, cool slightly, then sink again, driven by heat escaping from the planet's center. This motion is anything but calm. It twists, folds, and loops through itself, forming immense vortices that stretch thousands of kilometers wide. The core pulses like a beating heart, and with every motion, electrical currents are generated. Those currents create the magnetic field that surrounds our planet. It is a natural dynamo, a planet-sized engine of spinning metal, turbulence, and electricity. But like any engine, it is not perfectly smooth. It wobbles, it stutters, it surges, and sometimes those internal movements shift enough to disrupt the magnetic field above. A reversal begins not with an explosion, not with a sudden collapse, but with an imbalance. Somewhere deep within the core, a powerful current changes direction. A rising plume cools, a sinking plume warms, a spiral twists the wrong way. The magnetic field weakens slightly at first, so slightly that no one on the surface would feel it. But the weakening grows, and as it does, the poles begin to drift magnetic north. The point our compasses obediently follow starts wandering faster and faster, no longer content to sit near the Canadian Arctic. It races towards Siberia, accelerating each decade. Magnetic south drifts too, in its own unpredictable path. This is the first sign. A shuffle, a drift, a subtle unraveling. But soon, the weakening becomes more dramatic. Instead of two stable poles, Earth begins to form several. One near the Arctic, another over the Pacific, a third emerging near the equator. The magnetic field fractures into patches of strength and weakness, swirling like smoke in the wind. A compass would not simply point the wrong way. It might point toward a different pole entirely, then swing again as you walk forward. To ancient humans, such a world would have seemed supernatural. To modern civilization, it would be deeply unsettling and profoundly disruptive. As the field weakens, more charged particles from the sun penetrate through it. The invisible shield that once deflected solar radiation becomes thin and uneven. Satellites in orbit begin to feel the difference almost immediately. Their sensitive electronics are exposed to higher levels of radiation. Glitches multiply. Some systems reset unexpectedly, others degrade faster than expected, shortening their operational lifespan. The South Atlantic Anomaly, already a dangerous zone, would grow larger, swallowing more of the sky. Satellites passing over it would need to shut down their instruments more frequently or risk permanent damage. Space telescopes, Earth observation satellites, communication networks, all would face increased failure rates. GPS signals, already fragile, would become less reliable, their precision eroded by the shifting magnetic field. Aircraft relying on magnetic navigation would need constant recalibration. Deep sea navigation, which depends heavily on magnetic readings, would become erratic and dangerous. On the ground, the changes would be subtle at first. Compass errors, unusual auroras glowing at mid-latitudes, faint but persistent disruptions in radio communication, pilots flying high-altitude routes near the poles, where radiation is strongest, would face increased hazards. Power grids, especially those at higher latitudes, would become more vulnerable to geomagnetic storms. And yet, through all of this, nothing catastrophic happens overnight. There is no day when the poles suddenly flip like a switch. A reversal is not an instant event. It is a process, a slow, chaotic transition that unfolds over hundreds or even thousands of years. Imagine a world where your great-grandparents lived under one magnetic north, you live under another, and your great-grandchildren under a third. The shift would be noticeable, measurable, sometimes startling, but it would be gradual. Still, the consequences accumulate. With the shield weakened, a strong solar storm, like the one that struck Earth in 1859, would deliver far more damage than it did then. Satellites knocked offline, power grids overloaded, communication cut, perhaps even widespread blackouts. The magnetic chaos below amplifies the chaos above inside the core. The turbulence continues. The molten iron currents behave like storm fronts inside a metallic ocean. Reverse flows form, streams collide. New regions of magnetism bubble up in unexpected places. The field fluctuates wildly, sometimes strengthening for a decade, then weakening again, and then, slowly, the process stabilizes. One of the emerging magnetic poles gains dominance and begins to pull the fading field into alignment. Over centuries, the field strengthens again, but now in reverse. North is south, south is north. The planet survives, life continues. But during the transitional centuries, the magnetic chaos phase, Earth experiences a world unlike anything modern humans have ever known. This is not a doomsday scenario. It is simply the physics of a living planet, a planet whose heart is always in motion, a planet that has rewritten its magnetic identity countless times before and will do it again. The question now is not whether the poles will reverse. They will. The question is how prepared we are for the century-long storm that comes before the new magnetic world settles into place. And in the next part, we step into that world, into the strange, dimming shield, and explore what it would truly feel like to live on a planet whose magnetic armor is failing. Imagine waking up one morning to find the sky glowing, not just at the poles, not only in the frozen north or the far south, but everywhere. A shimmering curtain of color stretching across the horizon in places where no aurora has ever been seen before. Green and purple rivers of light rippling over deserts, cities, jungles, and oceans. People step outside in disbelief, staring upward as the night sky flickers like a living flame. This is not a sign of beauty alone. It is a sign of change. The unmistakable glow of a magnetic shield that has begun to thin. A world living under a weakening magnetic field enters a strange era, one both mesmerizing and dangerous. A field weakened by 80 to 90% would let far more charged particles into the atmosphere, igniting auroras across the entire planet. Equatorial nations would see lights once reserved for the Arctic Circle cities, like Cairo, Mumbai, Rio, and Singapore, would stand under colors that once danced only near the poles. The sky becomes a reminder that the shield above has dimmed, but the beauty masks the danger. With the field weakened, Earth becomes more vulnerable to radiation from the sun and the cosmos. Normally, our magnetic field deflects most of these charged particles. In a weakened state, it cannot. High-altitude flights, especially those crossing polar routes, would become far riskier. Pilots and passengers would be exposed to higher doses of radiation. Airlines would reroute flights toward equatorial paths to avoid dangerous regions, increasing fuel costs and travel times. Astronauts aboard the International Space Station would face radiation levels far higher than what the station's shielding was designed to withstand. Space agencies would need to reinforce habitation modules, reduce time spent in orbit, or pause missions altogether during periods of intense solar activity. And then there is the aviation system itself. Modern aircraft rely on high-frequency radio communication when flying over oceans or polar regions, but those signals pass through the upper atmosphere, the very region most affected by increased radiation. Communication blackouts could become more frequent and more severe. Controllers lose contact, pilots navigate blind, flights divert, delay, or ground entirely during solar storms. Down on Earth, the consequences ripple through technology satellites. The fragile machinery orbiting above us are the first casualties of a weakened magnetic field. Their electronics, already vulnerable to radiation, face a constant barrage of high-energy particles. Over time, circuits degrade, solar panels weaken, instruments malfunction. The lifespan of satellites shortens dramatically. GPS systems, the backbone of global navigation, would be less reliable. Instead of pinpointing a location within a meter, errors could grow to several meters, then tens of meters, then more. Smartphones, shipping routes, agriculture systems, and emergency services all depend on GPS accuracy. A degraded signal becomes more than an inconvenience. It becomes a threat. Telecommunications satellites would experience interference, reducing the reliability of internet, broadcasting, and global communications. Some satellites might need to shut down temporarily during solar storms. Others could fail permanently. Meanwhile, power grids on the ground face their own challenges. Strong solar storms can push powerful currents into long transmission lines, overloading transformers and causing cascading failures. In a world with a weakened magnetic field, these storms strike harder, penetrate deeper, and threaten grids that were never built to withstand such forces. Regions at higher latitudes are especially vulnerable. Northern Canada, Scandinavia, Russia, and parts of the United States could experience widespread outages after intense solar events. Even mid-latitude regions would not be spared. A storm similar to the 1859 Carrington event, harmless in its time, could cripple modern infrastructure. Yet amid all these dangers, one truth must be understood. This is not the end of the world. The magnetic field does not vanish entirely. It weakens, fluctuates, and becomes chaotic. But it does not disappear. Earth maintains some protection, and even at its weakest, the field still shields the surface from the worst radiation life survived past reversals. Early humans endured the Lachamp event. Animals continued to thrive. Though their navigation may have become confused, the planet does not turn into a scorched wasteland. But disruption, that is guaranteed. Migratory animals, turtles, birds, whales, that rely on magnetic cues may become disoriented. Some species may adapt, others may struggle. Some might shift their migratory routes entirely. It would be a global biological ripple, subtle at first, then more pronounced as the field enters deeper chaos. Humans, too, would need to adapt. Cities at high altitudes or in weak field regions would monitor radiation levels more closely. Satellites would be built with stronger shielding. Space agencies would forecast solar storms with greater urgency, and power grids would receive upgrades to withstand geomagnetic surges. Navigation would rely more heavily on inertial systems rather than compass-based guidance. Daily life would continue, but with more warnings, more interruptions, more moments where the world pauses to deal with the fallout of a magnetic field in flux. The greatest danger of this era is not apocalypse. It is unpredictability, a world where the sky glows unexpectedly, A world where satellites fail at the worst possible moment. A world where a single solar storm can cause a blackout that takes days or weeks to repair. And this era would not pass in a year or a decade. A magnetic reversal unfolds over centuries. Generations would live their entire lives under a dimming shield, never knowing the stable magnetic world their ancestors enjoyed. But eventually, the chaos settles. The field strengthens again. A new north, a new south. Earth finds its balance. The question that now rises is, what happens when the weakened shield meets the greatest force in our solar system, the Sun, during one of its violent outbursts? Because when the Sun erupts while Earth's magnetic armor is thin, the results can reshape entire civilizations. The Sun has always been our giver of life, a steady furnace burning across the endless dark. But that calm golden circle we see in the sky hides a truth we rarely confront. The Sun is violent. It roars, it lashes out, it erupts with forces powerful enough to cripple a modern civilization. Most of the time, Earth's magnetic shield absorbs the impact, deflecting the chaos back into space. But in a world where that shield is weakened, in a world entering the magnetic reversal phase, the Sun becomes something far more dangerous. Every few minutes, the Sun releases flares, bursts of X-rays and ultraviolet radiation that flash through space at the speed of light. And sometimes it unleashes something even stronger, coronal mass ejections, or CMEs. These are colossal eruptions of magnetized plasma, billions of tons of solar material hurled outward at millions of kilometers per hour. When a CME hits Earth, it can compress our magnetic field, pump electric currents into the ground, overload power grids, and strike satellites with a storm of charged particles. Under normal conditions, Earth can handle most of these impacts. But under a weakened magnetic field, during the early stages of a reversal, the shield buckles. The Sun's storms reach deeper into the atmosphere. They become storms not of space, but of Earth. Imagine standing outside as one of these storms hits. The sky darkens. The aurora intensifies, no longer a gentle curtain, but a raging river of light stretching across entire continents. Colors pulse overhead, green, purple, and red, brighter than any aurora ever recorded. Radio signals weaken. GPS glitches. Power grids hum with electricity they were never designed to carry. On the ground, transformers heat and strain as geomagnetic currents surge through them. This is not Hollywood. It has already happened. In 1859, before electricity ruled our world, a massive solar storm struck Earth. The Carrington event, the most powerful solar storm in recorded history, set telegraph lines on fire. Sparks leapt from machines. Operators were shocked. The northern lights glowed as far south as Cuba. If such a storm hit today, with our weakened magnetic field, it would be far worse. In March 1989, a smaller solar storm triggered the collapse of Quebec's entire power grid, plunging millions into darkness for 9 hours. It took 92 seconds for the grid to fail. That was with Earth's magnetic field at nearly full strength. And then there was 2012. The near-miss A storm, as powerful as the Carrington event, blasted through Earth's orbit. But the planet had moved. We missed it by days. NASA warned that if it had struck, it could have knocked out satellites, destroyed transformers, crippled communication networks, and damaged global power infrastructure on a scale humanity has never experienced. Now, imagine a Carrington-class storm hitting during a magnetic reversal when Earth's shield is weakened by 80 or 90%. The consequences would not simply be stronger. They could be 10 to 100 times more intense. More solar radiation reaches the surface. More electric current flows through the grid. More satellites lose control. instrument systems would burn out. Navigation systems would glitch or fail. A single powerful CME could trigger what scientists call a global blackout scenario. Power grids connect continents, transformers, the massive devices that regulate voltage, cannot be replaced quickly. Some take months to manufacture. If hundreds failed at once, power outages could stretch from hours to weeks, even months in some regions. Water treatment plants, hospitals, communication networks, banking systems, transportation and food supply chains all depend on stable electricity. A major solar storm during a magnetic reversal would strain every system our civilization relies on. This is not an extinction event. It's not an apocalypse. It is disruption on a scale humanity has never faced. A technological crisis, not a biological one. We would survive, but the world would slow. Cities would dim. Satellites would fall silent. Navigation systems would falter. Supply chains would seize. The sky would glow, and the world beneath it would struggle to understand what has happened. And yet, humanity is not helpless. For the first time in history, we have the ability to see solar storms coming, days before impact. Space weather observatories, such as NASA's SOHO and the DSCOVR satellite, watch the sun constantly, measuring magnetic fields, particle flows, and flare activity. We can warn power grids, shut down satellites temporarily to protect them, and prepare aircraft for rerouting. Engineers are learning to build transformers with better shielding. Satellites are being designed with hardened electronics. Airlines increasingly monitor radiation levels along their routes. Space agencies study the core to better predict magnetic field changes. And as the field continues to weaken, global efforts intensify. Humanity's strength has always been its adaptability. We study the sun not because it is dangerous, but because it is essential. We map its storms because knowledge is protection. We prepare for the worst because preparation is survival. A reversed magnetic field will create challenges, yes, but it will also push us to innovate. Stronger satellites, smarter grids, faster forecasting, and more resilient systems. The sun will not relent, but neither will we. And when the chaos finally settles, when the poles complete their slow, centuries-long dance, and Earth emerges into a new magnetic era, the planet will stabilize. The field will strengthen. The shield will regrow. Which leads us to the final chapter. A world after the flip, a planet reborn, and what the future looks like when North becomes South, and humanity learns to live under a new magnetic sky. When the long centuries of turbulence finally end, the world settles into a quieter rhythm. The magnetic field, once fractured and chaotic, begins to organize itself again. The multiple wandering poles merge, strengthen, and align. The field regains its structure, not as it was before, but in reverse. North becomes South, South becomes North. Compasses, once spinning in confusion, now point in a new direction. Navigation charts are rewritten. The planet's invisible architecture has flipped, and with it, the magnetic identity of Earth has changed. But life continues. Civilizations adapt because adaptation is what humanity does best. Generations who lived through the dimming shield now watch as the magnetic field slowly regains its strength. Satellites are rebuilt with hardened designs. Power grids are modernized to withstand geomagnetic surges. Airlines adopt new radiation-safe routes. Space agencies refine forecasting tools, predicting solar storms with greater accuracy than ever before. Humanity emerges from the magnetic transition not weaker, but wiser. Animals adjust as well. Migratory birds, sea turtles, whales, and countless other species that rely on magnetic patterns to navigate experience confusion. At first, some migration paths shift. Some species adjust through instinct and evolution. Nature finds new balance. It always has. Even during the Lachamp event and ancient reversals, no global extinctions occurred. The living world bends, but it does not break. The long-term effects settle into something ordinary. A compass pointing south is no more strange than it once was, pointing north. Maps are updated. Humans accept the change, the way we have accepted every change the planet has ever given us, from shifting climates to rising seas to drifting continents. A reversed magnetic world becomes normal, and life builds upon it. And as we look at this new world, we recognize something profound. Earth has flipped its poles hundreds of times throughout its history. This reversal was not an ending. It was a transition, one chapter in a far longer story, a reminder that the planet is alive beneath our feet, always moving, always changing, always evolving. The magnetic field is not a fixed shield, but a living system shaped by the molten currents deep inside the core. It shifts because the planet itself breathes. The true marvel is not that Earth changes. The marvel is that we, fragile and temporary creatures, are able to understand it. We learn to read the magnetic signatures trapped in volcanic rock, unlocking the diary of ancient fields. We built satellites to watch the sun, predicting storms before they strike. We measured the drift of poles, tracked anomalies, and calculated the strength of our weakening shield. We prepared, adapted, endured, not through strength, but through knowledge. This is humanity's great story: to take forces as massive and ancient as the Earth's core and the sun's fury, and find our place within them to survive not through instinct alone, but through curiosity. Curiosity is the force that moves us. Curiosity is the shield we build for ourselves. Curiosity is what allowed a species born on the surface of a small planet to understand the heartbeat of the world below. As the new magnetic field stabilizes and the sky returns to its quiet darkness, we look up with the same wonder our ancestors felt thousands of years ago. The stars shine as they always have. The sun rises on a planet that has turned itself inside out and yet continues to spin, cradle life, and offer mystery. And in that mystery, we find who we are. Because even as the poles shift, even as the world changes and the shield above us bends and reforms, one thing remains unbroken: the human desire to know it is this desire, fragile, brilliant, unstoppable, that carries us through every cosmic challenge. It is what lets us understand the past, endure the present, and step into the future without fear. The magnetic world will change again someday. The poles will drift, weaken, strengthen, and flip once more. But humanity will still be looking upward, still asking questions, still seeking meaning in the thousands of miles of molten metal and the infinite stretch of space beyond. Because the story of Earth is not the story of endings. It is the story of movement, the story of light in darkness, the story of a species that survives by understanding a living world and continues to wonder at all it reveals.